All right, so we kind of touched upon how exactly classification works last time. So let's do a quick recap of what exactly we discussed in terms of logistic regression, right? So we saw that when we wanted to predict a class, train a model that predicts two different classes, like let's say different types of cancer or tumor, if it is malignant or benign, what we looked at was linear regression or any kind of linear model doesn't really work. Because when we have such a data distribution, and then we start with a linear model with existing data, and then if an outlier comes in, right, then the decision boundary shifts altogether. So this is something that we really don't want to observe when it comes to any kind of classification. We want the decision boundary to kind of stay consistent. So what we looked at was we looked at how can we look at another function, mathematical function, which also utilizes linear uh, distribution. It stays in the backend that the data is distributed linearly, but we are modifying the functionality of this linear data into a sigmoid function, which does look like this. So even when there is an outlier data point in either of the classes, it does kind of take care of those outlier points. So how do we define this, right, in terms of math? So a sigmoid function is this. We look at a linear equation, equation of a line, which we fit into the sigmoid function, and then that becomes our model y. And then we have a boundary condition that is defined by the threshold, which is if it is greater than or equal to 0.5, it becomes class 1. If it is less than or equal to or less than 0.5, it becomes class 0. So once this is with this basics of building a model, we looked at how can we train this. We realized we can't use mean squared error because can anyone give me the reason why we can't look at mean squared error based on what we discussed last time? So with mean squared error, we didn't have a convex curve, right? That is what we want to observe when we are looking at training a deep or any kind of machine learning model. We want to observe a convex curve. So what exactly is a convex curve? For example, this is how we defined our cross entropy function or cross entropy loss, right? And the left-hand side of the curve looks like this, and the right-hand side of the curve looks like this. So when we combine both of them, it looks like this, right? And this is our generalized loss function that we can use for training. And when we want to train this, we have a convex curve. This is how the curve looks like. But when we have mean squared error as the loss function for logistic regression, we have a curve that would look something like this, right? So because of that reason, the gradient descent wouldn't occur smoothly, and then it would get stuck in local minimas, and it wouldn't get to the global minima, right? So what exactly we mean by descending, right? So this is what is happening where we are defining a set of weights and biases values, and then what we want to do is like get that random initialization to a point where it can generalize across different kinds of new data points as well. So with this kind of base for classification, today we'll be exploring more different types of classification algorithms. We'll understand why we need those kind of algorithms as well. But before we move ahead, does anyone have any questions with respect to logistic regression? All right, so jumping ahead, what we'll be looking at today are two different types of classification algorithms, which is k-nearest neighbors and support vector machines. So why do we need these algorithms, right? So you learned about logistic regression. If that is enough, why are there these algorithms as well? So can anyone think about any reasons why we are looking at these algorithms today? Any guesses? Random guesses are also fine. Okay, so basically we assume that there is a linear relationship between the input data and the output data, right? So what we say is like if x is equal to y, that is a linear relationship. But what if that is not the case? What if if the input and the output are not related linearly, if they are related quadratically or in some polynomial scale? So how do we look at such kind of data points, right? And another one is that the decision boundary is always a straight line, right? So if you remember, I showed the decision boundary on a logistic regression, it is always a straight line. So again, that might not work for all the different cases that we are looking to solve as well, right? So that is where these two algorithms kind of address partially these challenges. So let's quickly jump into what these algorithms kind of do. So going into k nearest neighbors. So we'll take the same data set that we looked at, which is the iris data set. We have 3 different types of iris flowers, right? And how are these characterized? The length of the petal might be different, right? And the length of the sepal might be different, which is the green part that connects to the stem, right? So these are the main characteristics of how these flowers are kind of differentiated, right? So with this problem or classifying these 3 types of flowers, how do we set up a problem statement, right? So if we take a feature of petal length and then the petal width, if we plot all these 3 different flowers based on these features, it might look something like this for class 1, class 2, and then class 3, right? And then why do we train machine learning models? Basically, we look at some sort of test data that we want to predict, which is not seen by the training data altogether, right? So let's put in some test data as well over here, right? So this is how the categorization occurs. So how can we use k nearest neighbors algorithm to kind of classify what exactly is the class of these test data points, right? So that is what we have been doing so far, right? So how can we decide what exactly these classes are? Can anyone think about it based on the definition of these, the name of the algorithm? It says it is k nearest neighbors, right? So why is it k nearest neighbors? Uh, Not really, but it is close. Anyone else has any guess? Exactly, right? It is not the number of clusters that we form, but it is the number of uh, actual ground truth values that are near to the test points, right? So what does that mean? So again, let's take the same data distribution over here, and then let's just take 3 different test samples over here, which are in purple. So how can we determine the classes is by looking at its nearest boundaries, right? And if we are not convinced by the number of samples that are present in the smaller circle, we might want to look at a larger area as well, and then see if there are more examples that are close by that define what could be the class of these new test data points. So how do you think we can figure out what exactly is the class of this? Number of nearest points is correct, but how can we compute that? Here we are looking at it visually, right? But if you go in the back end, it's just math numbers, right? It's columns of numbers. So how can we define what exactly is the class of this? How can we compute that? Exactly. So distance is what we look at in computing what is the class of these points. So how do we do that? We look at Euclidean distance, right? So how does Euclidean distance with the test data points that we are already looking at and the training data points, how can we classify the class of these test points? Let's look into that. So what does k nearest neighbor mean? What does k mean? Can anyone give me an example about it? What is k? Yeah, it's as simple as saying that it's a scalar number, right? Like all we look at is, let's say we are looking at the 5 nearest neighbors from the test point, and then based on the value that is the distance that is present from the test point to the 5 nearest neighbors of the test point, we classify if it is class 1, class 2, or class 3. So let's look at examples of how this is done. Let's take this set because we have a k value of 5, right? We have our test point, and then we have 5 different training data points, which are of class, let's say, some class, which is class 1, 2, 3, any of those classes, right? So how we compute the distance between these 5 points to the test point, and then we identify what exactly is the class of these ground truth points, and then we count how many data samples are there nearest to it, right? So we get a count of for each class. For class 1, it is 0. For class 2, it is 0. For class 3, it is 0. So by looking at this, we can clearly say that the test point belongs to class 3 over here, right? So let's look at another example over here, which is this, right? So what do you think is the class that it belongs to? Again, we go ahead with the distance computation, right? And then we look at all the different classes it belongs to, the nearest points, and then we look at classifying it. So based on these counts, right? So I see a mismatch here. This is class 3, not class 1. So if we have 3 points belonging to class 3 and then 2 of them belonging to class 2, how do we classify this as? Which class does this test point belong to now? It's just the max value. Then it will become class 3, right? Now let's look at another example, right? Which is this. We have again the same, compute the distance, look at all the classes, and then count. But here's the tricky part, right? So we are looking at just, we can ignore class 1 because it's just one data point. But between class 2 and class 3, we have 2 points each. So in this scenario, how do you classify which class does it belong to? How do you define that? Yeah, as simple as that, right? So we look at the closest classes, and whichever has the minimal, like the least distance, that is the class that we consider. Suppose you're not convinced by this, what can you do? If you're not convinced by this number, because 2 classes have the same distribution over here, where class, this test point could be class 2 or class 3. We do look at the distance, but we are not convinced by it. So how can we prove that it belongs to class 2? Exactly. Just increase k from 5 to 7. Can we have a k value of 4, 6, 8? Do you think we can have a k value of 4, 6, 8, 10? Or should we have the values of k as odd numbers or even numbers, basically? Doesn't matter, right? So here we are looking at 3 classes. Sometimes we might be looking at 5 classes, or sometimes we might be looking at 10 classes. So doesn't really matter if you're looking at even numbers or odd numbers. So sometimes I have heard theories where it says that we need to have odd number of k values because it is easier to differentiate, because we can have a differentiating factor. But that is only true if you have 2 classes. But if you have more than 2 classes, that goes void. So doesn't matter what the value of k is, you can have any value of k. And then if you compute the distance, you'll have the class of the test data point. So now the k nearest neighbors is all just this, nothing more. So what do you think is the difference between linear regression, logistic regression, and k nearest neighbors? What is different over here? Because we have gone over linear regression, logistic, and then also now we looked at k nearest neighbors. With all these 3, there is something that is very unique to k nearest neighbors. What do you think that is? Uh, we are looking at the features in a different way, but that's just data representation, right? It has in no way affecting what the algorithm is. So, but there is a very like clear differentiating factor between k nearest neighbors and linear and logistic regression. So I'll give you a hint. If you look at linear or logistic regression, we had weights and biases. We were randomly initializing. So So with that initial hint, can you think about what could be the difference between those two and k nearest neighbors? And another thing that we did cover was gradient descent as well for logistic regression and linear regression. Now, are we training any model over here? So what does training mean? We are changing the values of weights and biases. If we look at the linear equation, which was z is equal to wx plus b, we were initializing with some value for w, and we were initializing some value to b, right? And then we were varying the values of w and b by looking at some kind of training where we were comparing the distance and then changing those values. But what are we doing over here? We are not looking at any of such sort of mechanism over here. All we are doing is we take the distribution of the data, we just put it out there on a graph or some sort of representation. We take all our test points, and then we compute the distance, and based on the k number of nearest neighbors, we classify it already, right? So we are not even looking at training over here. So that goes to prove that you can look at statistical models. So k-nearest neighbors was one of the first statistical models that was developed, right? And that kind of led the revolution of what we look at in terms of machine learning and all of that these days. But back then, with just math, you were able to look at some sort of a machine learning based algorithm. Right? Isn't that fascinating, where you're not even training a model, but still predicting what exactly a class of a data point is? Right? So how do you define KNN then? Right? So KNN is nothing but it is a simple, non-parametric, supervised machine learning algorithm used for classification tasks by finding the k closest data points to a new data point and using their labels or values to make a prediction. It's as simple as that. We don't have to look at training the model. We don't have to worry about gradient descent. We don't have to worry about computation of losses, any of that over here. It's just one metric, distance, right? So we looked at Euclidean-based distance. You can also look at absolute distances as well. You can look at Manhattan distance. So there are a lot of distance metrics that you can consider instead of just Euclidean distance. So now you know KNN. Any questions with respect to KNN? Right? Cool. So what we'll do now is we'll jump into the coding of KNN. Let's look at how exactly we are building, because we have gone through a lot of theory with linear regression and logistic regression, but we haven't delved deep into coding. But let's do that today, right? So what I have done is I have already created a template. So if you go to our website, ais-asu.com, go to events page, you'll already see a template over there. Open that, create a copy onto your account on Collab, and then we'll start coding. So if you go over here, this is the Collab template file. Can everyone just give me a thumbs up once you have created a copy of it on your drive? Yeah, cool. So if you don't know how to do it, just open this, go to File, and then save a copy in Drive. Cool, good to start? Okay, so I have already implemented a couple of things that makes it easier for you. What we'll be doing today is mostly looking at the code, right? And then we have a couple of blocks where we need to implement things. Like we'll look at it interactively, we'll discuss about that, and then we'll try to implement what needs to go there. And then rest of the training code and everything is ready. So once those, wherever it says your code here, once we have filled those parts, you can run the entire code base and then it should run pretty smoothly. Yep, cool. So going ahead, so you don't have to worry about any of the imports and you don't have to worry about the 2D plot that we have defined over there. Let's jump directly into the model, right? So whenever we are looking at the model, what are the values that we are expecting to get? What do we need to define? Okay, right? So all we need to do is, so before that, is everyone aware of how to code in Python? Yeah? Okay, cool. So first step in any KNN model, what we need to do is basically initialize that K, right? So that's what we'll do over here. Now, to train the model, what do we need to do first? What does the fit function do? Fit is going to just basically compute the distances, and then it should give us what is the class that particular test data point belongs to, right? So let's come to fit function later. But before that, let's look at how can we define Euclidean distance, right? Can anyone tell me how you can define Euclidean distance over here? Yeah, yeah. No, we are looking at Euclidean distance, right? So Euclidean distance is x1 minus x2 whole square root of that, right? So what we have already here is we are just expecting 2 points, right, which is x1 and x2. We just compute the distance with respect to that. And how do we do that is just this, where what it is doing is it is computing the sum of all the possible x1 and x2s, right, and then computing the square root of it. If we have more than 2 features, we will have more number of x1 and x2s, right? So it is taking the square root of that and then returning the distance for us. Yeah. Oh, yeah. Sure. Oh, yeah, sure. So let's jump back into the math equation quickly. Sorry, I'll get back to the code quickly, which is this, right? So we do x2 minus x1 whole square plus y2 minus y1 the whole square. How many features do we have over here? 2 features. X is one feature, y is another feature, right? But what if we have more than 2 features? We need x, y, z, a, b, c, right? So that is what we are doing over there. We are summing it up all for uh, all the possible features. Instead of just having two, irrespective of that, if we have like 100 features also, that equation takes care of the uh, Euclidean distance with respect to all the features that is available. No, x1 minus x2 is the difference between your test value versus the training value. If you look at this 1 point is x1 and this is x2, right? And we compute the distance between these two, right? And then what is the feature space for this? We are looking at petal length and petal width. We have another two features as well where we are looking at sepal length and sepal width, right? So if you want to use those features as well, the data would change, right? So to compute with those features as well, so this test data will also have sepal length and sepal width, right? So if we plot it with respect to that, we again can compute the difference between those two, right? So what you're looking at here in terms of Euclidean distance is the traditional graphical representation of Euclidean distance. But when you're looking at features, you have the value of that point already, right? So you just compute the difference between the value of that test point at that feature versus the value of that feature of that training point. Is that clear? Yeah? Okay. So let's jump back into it. Cool. So now let's look at how exactly we can predict for one class, right? So we are looking at, we know how to compute the Euclidean distance now. Now what we need to do is we need to predict the class of 1 point. So how do we do that? Let's try and implement that. So can anyone explain me what is happening in that line? Yeah. So what we're doing over here is we are taking all the extrain values. So here, if you look at this, is everyone done implementing this line? Okay, cool. So if you look at this, how many extrain samples do we have over here? 5. We have one test set, which is the diamond over there, right? So what we are doing in that code is we are computing the distance of each star with all the 5 training samples and then having a list of those. So if we have 100 of the training points, we will have 100 entries in that list, right? So here we are restricting it to number of samples that are around it because we have already defined k, but there we have not yet defined how to use the top k values or the least k values, right? So that is why we are just computing all the distances that we can compute with respect to all the training samples for one test set, or rather one test point. With that defined, Now we need to look at the k nearest neighbor locations. Uh, what are those data points that we can look at, right? So for that, yeah, yeah, it is not necessary to use that in this one. That is an object-oriented construct. Do you know, have you studied about that? No? Okay. I won't jump into the details of it, but as of now, you don't need to use that self there, but we'll be using self elsewhere. Anyone else has any other questions with respect to what we have done in the next line? Arcsort does minimum to max. Yeah, so in Python, how indices work is it starts with 0 and then goes till, if you have 100 values, the pointer starts from 0 to 99. So it has 100 values there, right? So what we are doing over here is go from 0 to 5, but the fifth value is not considered. So that's why we have 0, 1, 2, 3, 4. Yep, cool. So now looking ahead, now we know what exactly are the locations of these data points. So can anyone tell me what does indices mean over here? Why are we looking at in like the location of these data points? So if you look at all the, so how are these values located? Or let's say, how are these values presented to us in terms of a tabular format, right? So this value could be in the 10th row. This one could be in the 20th, 25th, 29, and then 32. We need to know which row it is exactly present in, right? So that is what that indices is giving us. It is giving us where exactly what is the row value that these points are present in, right? So based on that, we look at the k nearest indices, and then we look at what are the labels of these points. That is the next step. Next, when you have all the labels, we did see that there is a possibility of having more than, like in that distribution, all the possible classes. Like let's say if we had 3 classes, but when we looked at 5 nearest neighbors, we had a possibility of getting all 3 classes as well. So next, what we are looking at is also the counts of these classes as well. So that is what this most common is looking at, right? And then we are returning the most common class value there. Any questions so far? So now what we have done is basically we have looked at predicting what class one data point belongs to. Now we need to look at all possible, basically all the test data points, right? So how do we do that? We look at predicting the entire sequence of test points now. I would request you all not to use the autocomplete feature on Collab, because if you use that, you won't understand what exactly you're coding. So please try and type each and everything there. Any questions on Zoom? Yeah, yeah, that was my question. So what do you think are the capital X and capital Y there? No, just go back to what we discussed in logistic regression and linear regression. What were capital X and Y? They were the training points, right? So that is what we need to define next, which is where that code goes over here, right? Self dot X train is this, and then Y train is that. If any of you are facing issues with coding, call us. We'll come around and help you out. Cool. And then we are done with developing the KNN model, training it, and then how are we going to predict it as well, right? Just let me know once you're done so that we can go to the next block of code. Or if anyone has any questions, let me know as well. Good to go? Yeah, okay. So we haven't run any of these cells. Let's just run them. You can go and then click at this play button or just do shift enter, it'll run those cells. So now what we need to look at is how do we load the data set, right? And then how do we get the training data set, the test data set, and then how do we predict the classes of the test data set, right? So to do that, we have already loaded the data set into wine. So here we are looking at wine classification, not the iris classification. So we load the wine data into wine variable, and then we look at getting all the X, basically the training data points, which is wine.data. And then the target is wine.target. Okay, here's an interesting question for all of you. So we have looked at normalization in a lot of other cases. Why do you think normalization is more crucial compared to linear regression and logistic regression over here? First question, does everyone remember what normalization is? Okay, so what is normalization is basically if you have, let's say, a feature value that goes from value 0 to 100, right? That is the range of values. And then you have another feature where the values go from 0 to 10. There is a huge difference, right? Like let's say you multiply 1 with 1, you get 1. But if you multiply 10 with 100, you get 1,000. So the difference between 1 and 1,000 is pretty huge. So whenever you're training, this large value will kind of make sure that it is the most prominent value, and then doesn't really give importance to the smaller values. So what we want to do is we want to bring all of these values into the same scale. We want to bring 0 to 10 into 0 to 1, and then 0 to 1000 into 0 to 1 as well, right? So with that definition of normalization, why do you think it's way more important over here? Why do we have to scale? So for linear regression or logistic regression, if you didn't scale, it would have worked. Probably the accuracy wouldn't have been that great, but it would still have worked. But here, would it work? What are we doing over here, basically? We are computing the distance between the features, right? If one feature has a really huge value and the other feature has really smaller values, that kind of the larger feature value kind of dominates the entire distance computation. So let's say if we were to look at the example in the PowerPoint where we had this representation, right? And without scaling, the blue class was very close by, but the green class was super far because it's larger distance, or the number value is large. We wouldn't have been able to classify it as class 1, but we would have classified it as class 3 because the distance is smaller. But in reality, it belongs to class 3, or rather class 1, right? So that wouldn't have been possible if we don't normalize it. So that is where the essence of normalization comes into picture, and that is what we are looking at using standard scalar over there. So we look at scalar.fit. So, okay, quick question. How can we normalize the values? Any idea? So you can look at taking the max value and the min value, and then taking a min-max normalization where you do a x minus x min divided by x minus x max divided by x min minus x max. That way it goes to a scale of 0 to 1 by default, or there are other statistical ways to do it using computing the variance and standard deviation, which let's not go into all of those things, but you can look at those things by yourself outside of these sessions. So yeah, so normalization is to bring, let's say you have we have two different features, which is petal length and petal width. Petal width can be between 0 to 10, but petal length values can be 0 to 100. Some of the petals are really long, some of the petals are small, but the width is kind of constantly varying between 0 to 10. So whenever you're looking at the distance between the test samples petal width, right, you would have a difference between 0 to 10, right? But let's say you go to petal length, you again compute the difference. You would have a difference between 0 to 100. And on top of that, you're squaring those values. So 100 would become 10,000, but your 10 would stay 100. So the dominance of petal length, so the classification of the test data would depend more on petal length, but it wouldn't consider petal width at all. So in order to make sure it considers these features uniformly, that is why we need to look at normalization. Yeah. Okay. So now we are done with the normalization. Now let's look at defining what the k value is. Because we have 3 classes, just giving the k value as 3 is not justifiable, right? Because if we get 1, 1, 1, doesn't really make sense. So let's go with 7. Right? And then initialize the class of KNN. And I assume it was KNN. If not, please use that class name itself. And then once you're done with it, you can train it. Whoops, I think I didn't. is that error? Let me resolve that error quickly. Predict one. Please make sure your spellings are right here, unlike me. And I hope that's the correct spelling. Yeah, it is. And then it should train. And that's it. You have trained your k-nearest neighbor class model, right? So similarly, there is a library called scikit-learn where all of these functions are already defined. All you need to do is something like this, where you import that k-nearest k-neighbors classifier, give the total number of k values that you need to take, and then you can look at the accuracy. So with our way of training, we were able to achieve an accuracy of 94.44. And with scikit-learn also, it is also giving the same accuracy as well. So yeah, what do you mean by scattered data? Mm-hmm. Okay. No, that is not how normalization would work, right? Normalization would kind of, so let's say you have a lowest value of 200 and then the highest value of 20,000. All the values would, 200 would become 0 and then 20,000 would become 1. Sure. Okay. So, okay, I want to add more to your question because with just the two data points you're giving, that wouldn't entirely justify what you're asking for. So that is where we look at outliers, right? The 200 is the outlier. If all the rest of the income values are between 20,000 to 40,000, and you just have one income value that is 200, that is one value, right? So technically, you don't really have to worry about it because what we're looking at is a generalization of our algorithm so that it can predict better for any new unseen data. With just having one value of 200 doesn't really justify to add a lot of weight to that 200 number. So what it would do is it would take that into consideration, but wouldn't really give a lot of prominence to that because it's already outside of the distribution entirely. Does that answer your question? So you can run the rest of the commands as well. Okay. I'll just show this, what exactly I'm trying to do over here, and then you'll have this code anyways later, so you can look at it. So what I'm trying to do over here is initially what we did so far, we just took two features, right? What I'm trying to do is how can we look at multiple features all together and then um, basically plot how exactly it looks like. So what you are asking, right, you can actually observe that over here as well. So if you look at the green points, there are a couple of green points over here as well, which are the outliers. But our model is technically not considering them at all because they're outliers. We can't really do anything about that, right? So there, in all data points, there will obviously be outliers. Sometimes you can remove them if you want to make the model really accurate, but we wouldn't recommend that because that kind of removes the possibility of generalization, better generalization of the model. So this is how the distribution would look like, right? Uh, you can actually go back to that same collab notebook that I had over there, right? And then I have saved this cell. You can copy this and paste it over there if you want to look at this observation in your notebook as well. Any questions so far? All right. So what I want you to do is I want you all to look at training the iris model, right? So I have given a boilerplate code for iris. I want you all to go through that code, define how exactly you can load the data set, scale the data set, and then train the model. We already have the model. Just make sure you are filling in the rest of these values. And then we have people around. If you're facing issues, call us. We'll come and help you out. But I want you all to do this exercise now. You have a question? I want you all to let me know once you're done with training the model on iris dataset. Here, so please try and get it running so that you can help me fill it up over here. Is anyone facing any issues? Good to go for the iris data set? Yep. Okay. I want you all to help me fill up these things. What is X iris? Yeah. Target one. Y iris. I'm not going to go. I want you all to tell me. Yep. And then scalar. How do you do that? Yeah. Is this correct? What it's recommending? Okay. And same for test. Should we take higher k value over here? Give me a k number over here. 15? How does 15 sound? Or should we go higher? Give a number. 17? 7? Okay. And then over here, KNN, K is equal to K value. And then train on scikit-learn. Was all of yours number the same as well? Yeah. And then I think this block was partially filled. I have fixed it, so you can copy paste from the template. And this is how our iris classification looks like. Done? This one? Anything here? Yeah. Yeah.
What is that?
You're looking for just one nearest neighbor. If that one nearest neighbor belongs to that class, it is just going to classify that it is that class. So let's say this is your training data and this is your test data. It is just comparing with that one.
That's why it's like basically fully accurate.
Yeah. It's not fully accurate. You're just getting it like that. Suppose if you look at this class is nearest to this. So basically, how do you compare with just one value? Right? You're comparing your itself with itself.
It's still like more accurate than like K or so.
But what if a new data point comes? Is that going to be accurate? So that is what we are training for. We are not looking to train for what we have. We are training for what we don't have. Yep. Cool. We are done with k-nearest neighbors. Any questions over here so far? So try increasing the k value to like 21, 30, and then just play around and see what happens, because we need to understand what are the limitations of k nearest neighbors as well, right? So I want you all to tell me what exactly do you think are the limitations of k nearest neighbors. Anyone? Two limitations, at least two. Can we have what do you all think are the two limitations of KNNs? Yeah, it's kind of a lazy learner, right? So it can't decide if it's this class or that class. If we are looking at 30 points and then we get 16 and 15, it looks at it's the 16th class. But if we do 32 points, if the other class is 18, it just shifts to that one. There is no defined way of saying that, okay, this is the correct answer or not, right? What else? What else do you think are the limitations? That is one. Yeah, compared to a lot of things, it is a bit more computationally intensive. Not in our current computational environment, but it is still the number of computation it has to do is pretty large, because what we are doing is we are comparing with all the training points that we have. If we have more than 1,000,000 training points, we are computing for each test with respect to 1,000,000 points, and that is going to increase the computational costs. Cool, right? So with these two limitations, can we overcome uh, these two limitations, but also overcome the limitations of linear regression, right? That is where SVM kind of comes into picture. So now jumping back into the slides, right? And then let's look at how exactly SVM works. Uh, Ready to go for SVMs? Do you have any questions? Oh, okay. So talk about that later. Let's jump into SVMs now. So let's again define a problem statement. So let's start with two different, like a binary classification problem here, right? Like let's say, let's look at fruit classification. We are looking at cherries and then apples, for example. We are looking at size and then the color. And then these are our apples, right? And these are our cherries. So just by looking at this kind of a distribution, we have explored KNN. We know we can look at the nearest neighbor and things like that. But is there anything else that we can do similar to linear regression or logistic regression over here to differentiate between cherries and apples? Yeah, you can draw a line, right? So let's do that. So again, taking the same thing, we draw a line. But how do we draw this line? There's already a hint on the slide. Yeah, so what we do is we take the, that's kind of true. What we do is basically for the nearest values of each class, right, which are the closest between themselves, we take those points, right? We draw those vectors, right? So these are the vectors that support that, okay, whatever is beyond this belongs to class apples, and whatever is below this belongs to class cherries, right? And then we compute the distance between the two and then draw a hyperplane, right? So these are our support vectors. These are indicating what exactly beyond this is, right? Beyond this is class apples, and beyond this is class cherries. So what exactly is a hyperplane, right? So for a 2D plane that we have over here, a hyperplane is a line. For a 3D plot a hyperplane is a plane. If you go to 4 dimensionals, it could be cubes, cuboids, things like that. So the definition of hyperplane is whatever is the n dimensions, hyperplane is n minus 1 dimensions. That is all the definition of hyperplane is, right? So how do we do this, right? So we look at the nearest points over here, take the distances, and then draw the line. As simple as that. That is how we look at SVMs. But what if we have outliers? We have seen outliers in KNNs, we have seen outliers in linear regression, we have seen outliers in logistic regression. So what do we do if we have outliers over there, right? Again, let's look at what are all the possible scenarios that we can have when we have outliers. Let's say this is we have this one cherry that is slightly bigger, and then more a red that is closer to apples compared to what we have seen the cherries are, right? What we can do in such a scenario, we can ignore that point and then just take a boundary that is going to be based on majority of the data points, right? Or what we can do is take the same setting and then have a boundary that exactly differentiates the classes. Here, it says that whatever is beyond this line is class cherries, and then beyond the above line is class apples. So what does this signify, right? Like we are looking at setting these margins with some sort of variations considered, right? We call such a margin called soft margin, where if there are some outliers, we don't really have to worry about it. But this is called a hard margin, where we want all the classes data points to be classified exactly what they are, right? So with this defined, this is pretty much how exactly we look at SVMs, right? But what we have over here is a distribution that is clearly separable by a straight line. What if we have a distribution that is not clearly separable by a straight line? Let's again look at a possibility over here. What if it's something like this? What can you do in such a scenario? Can you just think about it? Exactly, that's correct, right? You could draw a circle around it. But do you think that's feasible over here? So we are looking at hyperplanes. What is the differentiating factor? Like in the sense, what exactly differentiates between two classes is a hyperplane, right? What if you bend that hyperplane, right? So let's again look at that in a 3D plot, right? We increase that dimensionality in such a way that we are fitting that hyperplane, curving it around it, and then like putting it like a cup below all the apples or whatever the orange class is over here. So what we did over here is that we increased the dimensionality of the data points from 2 to 3 so that we are increasing the distance between both the classes, and then we exactly can have a plane separating the two. But if it were to collapse, what would happen is that the hyperplane would become like a bowl, right? So how can we achieve such kind of hyperplanes? That is where we are looking at nonlinear functions. If you remember logistic regression, what we did was we took a straight line and then applied a logistic function to it and then made it into a sigmoid function, right? So similarly, what we can do is we can apply multiple types of tricks to this in terms of polynomial kernels, or it could be a Gaussian kernel, right? Gaussian kernel is, we discussed what exactly Gaussian distribution is, right? And if we apply a Gaussian distribution to this one, we can achieve a better representation or better classification of our data, right? So could we consider using logistic distribution over here? Do you all think considering logistic distribution is a good choice or a bad choice? if you remember logistic distribution, it was something like this, where it peaked pretty high in the middle, and then the rest of the way it was kind of steep. But normal distribution was kind of a mountain or a hill, which is kind of going for a larger distance. What do you think about that? Is it feasible to have logistic distribution over here? He says no. Does anyone say yes? Or is everyone sleepy? Okay, let's look at what is logistic distribution again, right? Logistic distribution, where were the data points kind of lying? It were lying at the tips of that distribution, not at the center. But what we are trying to do over here is that we want to increase the distance between the point and the plane, right? If the points are already at the ends, we can't increase the distance between the ends and the points. If we center all the points in the center of the distribution, and then if we draw a much bigger curve around it, we can say that, okay, this is where in the center of the distribution, that is where most of our data point is. Whatever goes outside does not belong to this distribution. And that way we can say that logistic distribution is not a good fit for any kind of a kernel trick. And that is why we are looking at Gaussian distribution, right? And then what if you have more than two classes? So far we have discussed only two classes with respect to SVMs, right? We have been differentiating them with respect to planes, but what if we have more than two classes? What do we do then? So let's take our iris classification as an example over here. These are our distributions. One way to look at is one class versus remaining all classes. It could be done with respect to class 3 or class 2 or class 1, right? Where we are looking at one class versus rest of all the classes. We are drawing a plane in such a way that it separates just one class, but all the classes, remaining classes are not really, basically they are combined together as one. Or what we can do is we can have one class distribution separated out, and then again implement another SVM kernel where it is going to separate between these two classes. And then this can keep going on depending on the number of classes that we have, right? And that's pretty much it with respect to SVMs. Yes. You use multiple kind of mathematical tricks to kind of make, well, rather mathematical equations to kind of make it feasible for multi-class classification. Yep. Should we, let's get into the coding of one of the classification of SVM, and then we'll stop there. So back into the code. All right. Again, most of the things are defined already. All we have to define is the SVM class, right? And then how exactly we look at training. We know how exactly we look at training and all of that. So let's just define SVM. So what I'll do is like, it is not as simple as we did for KNN. So what I'll do is like, let's implement the entire thing. And then if you have any questions, I'll explain those questions with respect to this class. Yeah. Oh, oh, nice. Okay. It's giving me everything that I want to do. Is everyone done with this or still typing? Yeah, this is the entire code of SVM. Oh, is everyone done with implementing it? Yeah. Okay. Does anyone want to take a try on explaining this? Okay. So what exactly we are doing over here, right? So with respect to SVMs, what we need, let's go back into the slides, right, quickly, and then look at this. So what we need to do is we need to define a line. What is the equation of a line? Y is equal to mx plus b, right? But here we don't have, it's wx plus b in terms of machine learning because we are trying to train what exactly is the weights and the biases, right? Or rather the slope and the y-intercept, right? And then what we need to do is we want to define the distance between the nearest or the farthest points in a data distribution for both the classes and compute the distance between those points, which are these two over here. And then what we want to do is we want to make sure that this margin is between those two lines, right? And after that, what we also need to make sure is that whatever value is beyond this, on the top of the yellow line is class 1, or below that is class of -1. There is no 0 or 1 over here, unlike um, logistic regression, right? So that is what we are trying to train. So what do? We initialize with a random line, right? And then we are trying to figure out what exactly are the farthest points. We take those farthest points. How do we figure that out? We try to compute the distance between all the classes over here, and then whichever has the least distance, we take those values. We then draw the support vectors. Once we have the support vectors, then we try to push our initialized line between those two support vectors. So let's look at this in terms of code. So that is what we are doing over here. First, we are collecting all the features, right? Once we have that, we are looking at all the features, convert them into a linear representation, which is using the wx plus b format over here. And then what we are doing over here is, if y of a particular sample, we multiply that value, because y could be 0, 1 over here, because we are looking at only two classes. That is what SVM is capable of. SVM is capable of classifying between two classes, right? That is what we established. So we take the two classes, which is either 0 or 1. If this value is greater than 1 or equal to 1, we give it a conditional value of true. If not, we give it a conditional value of false, right? Once that is done, we look at the learning rate, or the lambda parameter, which is defining the support vectors. And then we compute it with respect to the weights, what is the slope that we need to consider, and then we multiply it with the learning rate. This is where we are looking at the gradient descent of the line, right? This is where we are defining what exactly should be the weights value and the biases value. If the condition is not met, we also consider, we take the differentiation with respect to another term, and then we compute the values of w and b, right? And then we look at prediction, where we are looking at the line, right? If the values are above a line, we'll give it a value of 1. If the value is below the line, we give it a value of -1. That is where the np.sign is going to help. And then we're looking at a decision function saying that, OK, we are good to go, right? So this is how SVM technically works. And then now let's just define what exactly are our data sets. And then we look at how exactly the decision boundaries are defined and what are our support vectors with respect to the data set. Oh, I think I haven't run the code at all. So make sure you have run the code. I'll just look at the class name, linear SVM. Finally, okay. Finally, we got it to work, right? And then if we were to look at a decision boundary with respect to our function that we have written, it would look something like this. It looks super messy, right? Let me see if I have a better one. So the reason why it is looking like this is we are trying to represent multiple features in a 2D plane. That is why it is looking like this. But if you look at it from multiple dimensions perspective, you can't basically visualize it. So that is what we are trying to do over here. Try to bring that visualization down to 2 features and then try to see what are the samples that we are considering as support vectors and then how exactly it looks like. So whatever are the circled values are our support vectors, right? And then they are used to get the margins, and then using that, we look at the decision boundary, right? So, and then you can try it out for iris data set as well. And then I have a better representation for iris data, which I can show it to you quickly, right? This is how it looks like for iris data set. Here, we don't have a really hard margin. We are looking at a soft margin. That is why the margins are inside a particular class over here, whereas for the other one, it is on the boundary. And then if you were to consider for multi-class, this is how it looks like for that, where we first draw a boundary for one class with respect to all the classes, and then we go and then look at the other 2 classes, and then again draw a boundary with respect to that. So this kind of concludes our journey with machine learning in supervised learning, right? So what we'll be going ahead in the next session is we'll look at some sorts of unsupervised learning methods, right? And just that for next session. After that, we'll start looking at deep learning algorithms. Like how does neural network work, right? What exactly we do to train a neural network. And then once that we understand all of that, we'll go into deeper aspects as well, where we look at how does computer vision work, how does natural language processing work, and we'll also try to train a smaller fraction of an LLM, not like how big a GPT-2 is or a GPT-1 is. We'll try to train a smaller version of it, and then we'll jump into reinforcement learning. But today's session kind of concludes the supervised learning journey for machine learning algorithms, but we look at more of supervised learning with respect to deep learning in the next, after next session. Next session, we are looking at unsupervised learning. So if you're interested in that, so do feel free to RSVP into that. The QR code is right here so that we can remind you about that event once you're done RSVPing. Any questions? Cool. All right, then. Thank you, everyone, for coming. We know that there are a lot of events happening. Thank you for showing up, especially to our workshop today. Right. I hope you had a good time. And then we're looking forward to the rest of the sessions with all of you. Thank you. The food's outside, so you can go and get some food. But if you have questions, I'm right here. Once again. Thank you, guys. I'll be stopping the session on Zoom.